Good afternoon, Shanika. Did you see the daily quizzes up?
I do.
Sorry, I thought I was already in the Zoom meeting. I'll give you until 3:04. Enough time to finish putting these grades. And I'll go close that door. Unless Chris, if you want to go ahead and get up and do it if you're done. Don't close it all the way, just cracks. All right. The log answers in 5, 4, 3, 2, and 1. Log the answers. Now, let's get everyone in. Some people inserted multiple times. All right. What are your zero divisors? It's Z8. 2 and 4 are some nice easy ones to pick. So 6. Also 6. 6. With Excel. What do you multiply 6 by that gives you 0? 36, 6 and it's 36 is divisible by 8. So 36 mod 8 would be 0.
10, no. 4, no. 1 and 4?
Let's see, 6 and 4 is 24, which is yeah. So 6 and 4 would also be zero divisors. So 2, 4, and 6.
Well, I don't know about like this, that's right.
Mm-hmm.
So if I just did 4 and 2, is that wrong, or do I need like a next pair? Because I know it would be.
Oh no, that would just be a common separator list. Is what you're looking for here. You don't have to be so formal to put it in the set.
So just like 2 and 4 is fine. Do I have to go 2, 4, 6, or is it 2 and 4?
2 and 4 is fine.
Okay.
How many zero
I thought
divisors
zero
did I ask
divisors.
for? No. So it's just like how every element in its inverse are paired together based on that definition. But there are their own separate elements, right? And as we just kind of discussed, 4 isn't the only thing that I can multiply, or sorry, 2 is not the only thing I can multiply 4 by to get 0 under this operation. The other one was 6, right? So any combination of 2, 4, and 6 as your answers would be 5. All right, what questions I got? I'm going to give you one big warning. I know this is tough for y'all. These homework assignments are tough. But if you're going to Google and just searching and copying down what you see, it's pretty obvious to me sometimes when it's happening. And it's very obvious that it's not your work. Not your work is an academic integrity violation. Yeah. Stop. You know, a couple of y'all did it on the 7th homework assignment. Sadly, I'm just now catching it because I didn't realize I hadn't graded it. I'm afraid I'm going to find some on the 8th. If I see anything like that pop up on this 9th homework assignment, I'm going to give you a 0 for that assignment. Use higher assignment. Is that clear? Okay. If you need help getting kickstart on how you need to go about proving something, you can ask me. Google can give you advice, right? It's logic. But if you can't interpret it into your own logic, into your own words and your own argument, then you should not be using it. All right. Okay. Now the anger here. Better professor. So we're gonna keep working on rings today. Oh, somebody can zoom here, not zoom anywhere. So an integral domain is a ring with what other two conditions? Try to recap some of our definitions. I thought I stole screen share. The integral domain is a ring with what other conditions?
The zero property.
So commutative, and this gives us where we get to zero properties with integral domains. That's not what we use to define integral domain.
Or non-zero divisors.
It has, no zero divisors, not non-zero divisors. It has no zero divisors at all. There's commutative ring and no zero divisors anyway. Yay, now I got this picture up. So that's what it meant to be an integral domain, and we saw examples, and just kind of like what we talked about today, where we can have zero divisors, elements that I can operate together. They'll give me my additive identity element, but neither of them are the additive identity element, which means that as long as I have zero divisors, I'm never guaranteed the zero property that's unique. Okay, so we talked about some examples of rings in this last one. We're talking about saying I can essentially append two axes of integers together to create a new ring. And that second axis is just being represented by some number multiplied by square root of 2. And we could keep, where the rest of my notes? Oh, I left them in there. But I can go ahead and start us off. So an integral domain, we make sure that we have no zero divisors, which means that we get the inflation property. Part of the reason why we like using integral domains versus just straight up rings. So the theorem states is that I have A times B is equal to A times C. This is using that second operation of my rings. And I know at least when I'm multiplying them both by, don't die us. As long as I know when I'm multiplying them by is the not zero element, so as long as it's not the identity element for addition, then I know that B is going to be equal to C. Forgot that it's separated in notes because I was looking at them while I was trying to troubleshoot the laptop. So we're going to prove it. Let A, B, and C be elements of R, where R is an integral domain. A not equal to 0. Then, if we start with the assumption AB is equal to AC. Going to say, all right. Now I need to make a little bit of an algebra again. I want to start rewriting this expression or this equation that I have right here, so that I end up with B is equal to C. So I'm working in an integral domain. Do I have multiplicative inverses necessary? Right? That means that B and C or A would have to be units. And we're not guaranteed that everything is a unit inside of the integral domain. So I can't multiply like by inverses like we're used to. Go ahead.
When you're saying that A is not equal to 0, does that mean that we can't move the AC to the other side of like all equal to 0 and factor out the A? Because in that case, A would be equal to 0. That's what like, so basically we kind of do that, right?
So great observation and great manipulation. That's what we're going to end up doing. What happens if I multiply any element of a ring by the 0 elements? 0, right? So I can choose B and C to be two different things, but as long as I multiply them both by 0, the outcomes will be the same. 0 times, I mean, just think of in the integers themselves, purple, 0 times 2 would be the same thing as 0 times 3, because they're both 0. But are 2 and 3 the same thing? So we have to make sure what we're multiplying by is never 0, because 0 is canceling out all information. So that's where that assumption for A is not B equals 0 is coming into, or the motivation for it. But you also picked up on something that's very important that we're going to need to use further. Let's do what you said, which was subtract A times C from both sides. I'll have A times B minus A times C is equal to 0. And now what do both of those two terms have in common? I can factor out that A, it's the left distributive property that we've even proven interacts well when there's an additive inverse. But now I have two elements that are being multiplied together that equal my 0 element. But do we have any 0 divisors in the integral domain? No. So that means we have the 0 property that one of those two elements have to be 0. But what did we assume about A? What do we have to assume about it? Yeah. Since R is an integral domain, and A must be equal to 0, or B minus C must be equal to 0, but A cannot be equal to 0. So we get B minus C must be what is equal to 0. And what does that imply about B and C? I'll add C to both sides. We'll get that they must be the same elements. Starting to notice that some of the arguments that we make keep reoccurring. Maybe a little bit new coat of paint on them. But same idea, same trick, same logic. And cancellation property is a very desirable property. Right? That's what makes half of our algebra work. You can solve for X because of cancellation. You can solve for Y because of cancellation, whatever. But we have just shown that we only get cancellation property in integral domains. And why again would it not hold for just a ring?
That is supposed to be.
Yeah, well, that cancellation property, what this is proving in general. holds. which would then kind of get back to B is equal to C. The integral domain is a commutative ring with what? No zero divisors. Okay, so if I drop the assumption that this is an integral domain, I'm also dropping the assumption that there are no zero divisors. So there could be zero divisors. If there are zero divisors in a ring, that means I could possibly have two non-zero elements that I multiply together to get the zero. So then what at this conclusion, then A's got to be equal to zero, B got to be B minus C got to be equal to. But that still hold if we were just working inside of a ring. So the rings, we no longer get the cancellation property. And we said part of our motivation for all these rings is try to get an abstract framework for the set of integers under initial. All of the integers always have the zero property, whatever we're working with in an abstract setting should probably also have this. So most of the time we'll study integral domains, but interesting things can happen in rings as well. What questions I got? You want to ruin it for yourself?
No, because I'm tripping out because like that's the same exact proof I did on my homework. But now I'm thinking that it's wrong because we're talking about integral domain. But it's not a question to like big, it was just like an observation.
What's the one problem again? I read that like.
If we're really part of the unity, then we
So you can't use cancellation property inside of the ring. You only use cancellation property inside of the integral domain. Now, it depends in a sense on what the operation is. Because we have cancellation inside of groups. And if I kind of zoom in a ring, I know a ring is containing a group under addition. Remember that at how we kind of built, we have a ring, or we have a group with a single operation. We created a second structure, we just add in a second operation on set. Okay, so a ring is still a group with addition. We add on this extra multiplication, the operation called multiplication. There's two extra properties that can satisfy. Okay. So as long as your operation that you're dealing with when you're trying to apply cancellation law, it's got to be only for addition. Cancellation law for multiplication does not work. That's part of the reason why we got to always make sure that we're careful on which operation we're talking about. And similar to discussions Sinai and I were having earlier, right? And this is why we can't use just identity element anymore. Because identity element is for a single operation or a particular operation. So we say zero is the identity element for which operation of the group? Or sorry, of a ring, addition. Ring. And if we have a unity, I should just do multiple. If it has a unity. A, B, but whenever I'm using 0 and 1, these are just representations. I'm not saying it's the integer 0, I'm not saying it's the integer 1. I'm saying this is the element that acts like 0 in the integers, or this is the element that acts like 1 in the integers. All right, hopefully they get. Okay. There's one other extension we can make, and it turns out even the integers themselves that we work in are not always let me not try to paint a story here. Let me just give you the definition. We can tack on one more desirable property, even on top of an integral limit. So an integral domain is a commutative ring with no zero divisors. But what are we missing that we might want to have? So an integral domain is a commutative ring with no zero divisors. But what's missing that we'd like to have, at least in the rational numbers, the real numbers, not always possible for integers. An inverse under what operation? So we get inverses under addition just being a ring itself. So we already have those. But if whether it's a ring or an integral domain or somewhere in between, we're not always guaranteed to have multiplicative inverses. We have to have a unity. And then when you have your unity, you need your elements to be units. They need to have some multiplicative inverse. So we can tack on one more desirable property and create a new structure that we call a field.
I have a question.
Mhm.
So integral domains don't have unity and any multiplication?
So they can have unity, they don't have, not every element is a unit. Not everything has a multiplicative inverse.
Oh.
So a field is a commutative ring with unity. In which every non-zero element is a unit. Is that the second line? No, you're right. My ADHD is going crazy because I keep hearing the conversation outside and just wants to focus in on it. So I'm getting distracted in the middle of the writing. What was that, Jacob? That's kind of crazy. Yeah, so a field is commutative ring with unity, so we have to have that identity element for multiplication. But then everything in that set, and when I say non-zero, again, I'm not talking about the integer zero. I'm talking about whatever the identity element is for addition. So fields are pretty strict. They can only rationals, real, and there's other things satisfy it. You have vector fields, or if you got the very abstract definition of vector space, it's a collection of vectors with a field. Your scalars are coming from the field. You need to have multiplicative inverses for your scalars. That's one connection I can make. But the question I have for you is, notice that this definition, did I say a field is an integral domain? No. So I only said that a field is a commutative ring with unity in which every non-zero element is a unit. So how might integral domains and fields be related to each other? One says commutative ring with no zero divisors. The other one says commutative ring with unity and everything is a unit. That one is non-zero.
Oh, the inverse, that's what we're talking about earlier.
So, what do you mean? Can you elaborate?
Yeah, so basically definitions are almost opposite, so I was thinking that this is how we find the inverse over there.
So, how would you, let's take it back to groups. How would you define the inverse group? That concept kind of makes sense.
So,
They're not the same thing, does one have units?
No, they're not the same thing, but they are interconnected. But it turns out,
One affects the other.
yeah, so we gotta think of these as sets, right? There's sets with operations. There's gonna be conditions where integral domains are fields. There might be conditions where fields are integral domains. So there's some overlap between them. Because they both take a commutative ring and assume that there is an extra property attached to it. And there is some shared elements that are both integral field and or integral domain field. The easiest ones to prove without spending another like 2-3 weeks making definition, theorem, definition, theorem, and then maybe corollary or lemma. Is that finite integral domain for the field? As long as your integral domain has a set number of elements that is not infinite, then it's always going to have to be a field as well, which means every non-zero element in there is a unit. It has a multiplicative inverse. Let's prove it. I'm gonna let capital D be a finite integral domain. We're gonna assume that it has unity 1.
Wait.
That we're calling 1. Sorry.
Right? You could tell me like what's the N supposed to be, as I see it, like see if I can see it,
The N.
yeah, like what's going, like what's the.
Oh, so we're gonna show that any element now in this integral domain has a multiplicative inverse.
Oh.
Great question. Let's show every element in the integral domain has a multiplicative inverse. No, that's good. I should have done that initially. Thank you. That's just coming from, again, the field of commutative ring with unity, in which what?
Every non-zero element
Is a unit. And if it's a unit, then stacking definition on definition. What does it mean to be a unit? Not identity element. It interacts with the concept of identity element.
The unit is the inverse of that element.
Ring, but yes. And we also want to be a little bit more careful with language, right? When we say inverse, which operation? Multiplication. So a unit means it has its multiplicative inverse inside of the ring. Big breath, right? We got it. So I'm going to just choose some element for my integral. Someone give me a letter. B. Well, if B just happens to be that unity, then what is the multiplicative inverse of the unity? Well, that's the representation for it. But what is the element from any ring that I multiply the unity by to get the unity? Yeah, the unity itself, 1. So if I was just reaching into this hat blindly, and we call this hat a ring, it's full of all of our elements, and I just happen to pull out the unity element, I know I'm going to have its inverse there because it is its own inverse. So now that we kind of covered this case, we know how unity works, and we probably want to cover everything else. So what are we going to now assume about B?
It's not induction, right?
Not induction. Good question. Oh, I'm missing an E there too. Maybe I should just stay still.
That would be not one.
Yeah, perfect. No, perfect time. Almost like it was voice to text or something. Same with voice to transcribe. Yeah, just assume that it's not one. Well, if that's the case, just consider the sequence, not A, that's my notes, B squared, B cubed, and I just kept operating this element with itself over and over and over again. When I say operating again, I should be more particular. I really mean what operation? Multiplication. So I'm considering this infinite sequence. So every term in this sequence is just this element B being multiplied by itself a number of times.
Didn't stop at N?
No. Because I could keep multiplying B by itself infinite many times in theory. But what you're probably picking up on, we assumed our integral domain is what? Finite. So at some point, thanks to the pigeonhole principle, we're gonna have to start repeating. We're not gonna be able to create new elements. Right? This raising B to every power doesn't mean we have to hit everything in the ring, but whatever the sequence is creating, it's going to start repeating at some point. No clue where, but it will. So I can say, since D is finite, and thanks to the pigeonhole principle, which I'll write out in a second, I know there's going to be 2 exponents, I and j, with I being greater than j. Such that b to the I power has got to be equal to b to the j power. Go ahead.
Can you explain that a little more? Like, if I is greater than change, and y is equal to I is equal to change.
So there exists these two because I'm repeating, right? We said I'm eventually repeating the sequence. So if I said, just for example of repetition. This is the sequence that is made from just taking B and multiplying it by itself as many times as I could ever think of, and then all we're saying is at some point along the sequence, I can pick one index, first index I come across is J, and then I can keep going on, and I'm gonna see that same element appear somewhere later on in the sequence, and that will be my I. And so I know that at some point later on in the sequence, I need to see that same element appear. Which is why we're just saying, we know there exists somewhere, I can't tell you exactly. But somewhere there's gonna be two indices, one larger than the other, such that if I raise B to both of those powers, I'll get this in that. That makes more sense. But we're in integral domain. What did we just show we currently have? So not an integral domain.
Oh, that's a zero.
That is a property of integral domains. We can maybe take advantage of it, but I don't think we're going to in our proof. Let me help you out by writing this. Since I is greater than J, I can break up that B to the I power. I know there's going to be J multiplications of B times whatever else is there. B to the I minus J. And then technically, got a multiplication by my unity element on that right, which is 1, or represented as 1. A times B is equal to A times C, then what? So you're getting to cancellation problem, right? We just showed that as long as we are working inside of an integral domain, we have the cancellation problem. And I'm multiplying this expression on both sides by B to the J power. Which means by the cancellation property, we have B to the I minus J. It's got to be equal to what? My unit.
Wait, so how we change the name?
We don't have cancellation for rings. But I didn't assume that my set that I'm working on is a ring. I assumed it's a what?
That's not real.
Integral domains are a commutative ring with no zero divisors. So we're putting on 2 extra properties.
That means you will do cancellation too?
You get it, but not directly. You have to do a different version. But you get it for fields.
As a property?
Only how we must find one on that side and the other side.
So I'm just looking at, there's always invisible multiplication by one, right? I can always use this as invisible multiplication by my unity element, strength these other terms here. That's where it just kind of appeared. And for the recording, I'm doing finger quotes for appeared. Right? And then it's just to clearly show by the cancellation property what I'm left with on the left side, hand side, and what I'm left with on the right hand side of that equation.
Oh, commutative ring to do calculation.
No. Because we go back, and this is what I was trying to make sure, our arguments depended on making sure we had the zero property, which meant we cannot have zero divisors at all. I cannot have two non-zero numbers that I multiply together getting zero. And our argument said, well, one of them has to be zero if I have no zero divisors. So if I remove this condition of there could be, or remove the no zero divisors condition, open up the door to say there could be zero divisors, this entire argument we make right here goes out the window. Because I cannot guarantee you that one of those has to be zero. No, you're good.
Integral only has cancellation. If what?
Because of no zero divisors.
So this one doesn't have. That one did have zero divisors, but this one doesn't.
No, because we're assuming
Assuming I did.
it's an integral number.
Okay, fine.
Yeah, no, it becomes just like I have to make sure I can piece together all these definitions and terms. I get it, don't worry.
Oh,
You
because
actually-
it's finite. No, that's not why.
Finite's what's telling us we can just keep operating, be with itself over and over and over again. At some point, I'm going to start repeating.
Okay, hold on. You didn't read the first one, right?
So we're almost done with the argument. So what I'm gonna do is I'm gonna say, let's finish the argument. We'll wrap up, and then you and I can keep talking for a little bit afterwards, try to clear things up. Okay? So I not only get that b to the I minus j is equal to 1. I also get b times b to the I minus j minus 1 is equal to my unity element. But wait a second. B times some element is now equal to my unity element. What does that mean I now have? I have a multiplicative index. Thus, b to the I minus j minus 1 is the multiplicative inverse for my element b. I'm not trying to say I minus j minus 1 is equal to -1. Remember, we got to read our notation correctly. B to the I minus j minus 1, whatever that integer quantity is. When I raise b or operate b, multiply b with itself that many times, whatever the element is that's created is going to act as the inverse element for b under multiplication. Did I ever tell you what the element b was? It's just some arbitrary element. And I've shown you a way, you give me any arbitrary element, I can generate or tell you what its inverse element is. So I can call this little b a what? A unit. Therefore. Every element. in a Finite integral domain. Every non-zero element. Is a unit. Integral domain. Very good, Carissa. It's a commutative ring with no zero divisor. So I have a commutative ring. And I've now shown I have a commutative ring, and every element is a unit. So what can I call this set?
Up to you.
A field. Therefore. Finite integral domain. We call it capital D. Is a field. Alright, and that's where I'm going to stop the material for the day. I'll be extremely gracious to let y'all hear what you did early. That way maybe Carissa won't die on us. Really hope she's okay. Alright, but if you have questions, feel free to stick around and ask.
This is confusing, sorry.
A non-zero divisor is when A times B cannot be zero. You
So
get zero.
a zero divisor is an element of a ring R which that there exists some B in the ring that when I take A and multiply it by B, I get the zero. We want A and B to be non-zero. That's what it means to be a zero divisor. Right?
When you see zero element, you mean actually zero, right?
You what?
When you see zero element, you mean actually zero. You get zero.
So we're not talking about the integer.
Okay, that's zero.
We're talking about the identity element for addition.
That's the very bottom.
No, we're having a little bit of conversation because we're trying to clarify some things.
When you done the bottom, please? When you're done.
You hear?
Oh, okay, so it's the bottom.
Yeah, sorry, yeah, I'm done. Like, once that proof is done, we're done with new material. At this point, we're just sticking around trying to clarify some things. So, no more new content. We're done with new content. But I'm taking the questions.
I still don't get it. Why was we able to use calculation in the last one, but the top, you didn't, and also you made B minus C equal zero.
Because I knew I had no zero divisors.
In the top one.
Yes,
What the-
because the theorem, as the theorem states, let R be a what?
ring,
Nope.
integral domain, and
What does it mean to be an integral domain?
your commutative ring with no zero divisor.
No zero divisors. We need to bring no zero divisors. So I'm just trying to take that longer statement, condense it down into a term. Right? So I'm assuming a commutative ring with no zero divisors. And as long as I know that's the case, if I'm multiplying two elements together in the product, the outcome is the identity element for addition, we just refer to as zero. Then we know one of those two have to be zero. Because that's the only way I can make the zero element appear through multiplication.
But then like, then what's the point of saying no zero divisor? Like, that's not zero divisor right there? Like,
That's not a zero divisor.
no?
No,
Okay,
because B and C, we end up showing are the same thing.
oh wait, non-zero divisor doesn't mean not zero.
Yeah.
It means like a regular number.
Yeah, regular number. Something, that's why when we were doing the, on Wednesday, right? Let's go back to the example.
Okay.
No, that was Unity, maybe did I go too far? Yeah, there's zero divisor. Do you remember this example? 2 and 3 were zero divisors,
Okay,
right? Because they're not neither of those are my identity element for addition. But I
okay,
can still multiply them together to get that.
okay, so I get the top. Now the bottom. On the bottom, right? We was able to cancel, wait, left cancellation. We was able to do that. And then what you
You're
said?
talking, and I just want to confirm, you're talking about this part of the proof?
Yeah.
Okay,
Why you said we could I do that again? Cancellation part right there.
because we assumed our set D is a what?
Integral domain.
Finite integral domain, and since we know we're working, it doesn't matter whether it's finite, that's just extra thing for this, so we can build that sequence.
Mhm.
Integral domain part is the more important part, because if I have an integral domain, I know I get cancellation.
Yeah, so I'll integral domain to the cancellation,
That's what we proved,
but not a ring.
not a range.
Okay, that would do that.
And integral domains are a specific type of ring.
So that proof was basically proving we could do cancellation. That's why you didn't use cancellation.
Yeah.
Okay, thank you.
Yeah, well, I can clarify. No. Not unless you cough 3 more times. So that is just me rewriting what it means to be a zero divisor in a harsh, bad way. So you can ignore that.
I like your definition.
Hmm?
I like your definition.
All right, any other questions?
No.
Okay. Tanika, did we lose you already or are you still here?
No, I'm still here.
All right, were you
She asked the
following
question,
along with that?
and yeah, I was.
All right, cool.
If anything, I'll send you an email later this evening or sometime tomorrow on the finalization for the 29th.
All right. Cool,
Okay.
thank you.
All right, have a good weekend.
You too. Danger, you still need this up.
Oh, yeah, like the last part, which is something.
Stuff real quick.